Hello everyone, I hope you are doing well. In this video, we are going to find out linear density for directions in simple cubic unit cell. Okay, the directions that we are going to consider are 1, 0, 0, 1, 1, 0, 1, 1, 1, and 1, 1, 2. And if you want me to do it for different directions, like to calculate linear density for different kinds of directions having different Miller indices, which could be like 3 to 1, 5 to 1, etc. If you want me to do that, simply comment and I'll do that. So let's quickly get started with our video. First of all, we should know the formula that we are gonna use to calculate the linear density, and this formula is general and can be used for any kind of cube you are considering. For example, whether it is simple cubic, body centered cubic, or FCC, face centered cubic, or other unit cells like hexagonal, tetragonal, whatever it is. Okay, this formula is general and is applicable for all kind of cases. So let me write the formula. Linear density, let me denote it by lambda sign. Okay, and in subscript we can write the directions whose linear density we are gonna calculate. Okay, this is something that I'm writing in subscript. It's totally up to you if you want to write it or not. You can simply use lambda sign, but it's better to use that notation because it will help us to differentiate which linear density we are calculating, like for which direction we are calculating it. That is equals to lambda HKL equals net number of atoms lying on the line, or total number of atoms lying on the line divided by the length of the line inside a unit cell you are considering. Alright, so this is the simplest formula. We can equivalently represent it using the symbolic notation. We can use capital N for net number of atoms lying on the line divided by capital L for the length of the line inside the unit cell. Here, linear density in our case is also known as linear atomic density, and this is the main formula that we are going to use, and this is the formula number 1. We'll be using it for finding out the linear density used for all kind of directions we have. Alright, so let's start with the first direction, which is 1, 0, 0. First we have 1, 0, 0 direction. Okay, whenever you are finding out the linear density, the first step is to draw the direction inside the unit cell. Okay, after drawing the direction, you will be able to calculate capital N and capital L for it, and doing so and putting it back into this equation, you will find out the linear density. Okay, so it is really simple. So let's start. First is to draw the direction. First step is to draw the direction, and we have these Miller indices. The first index shows the x coordinate for the direction, and the second index gives the y coordinate for the direction, and the third index gives the z index of the direction. First is 1, second is 0, third is 0 again. Okay, and you know how what direction looks like. It has a tail and a head. So where will be the tail of the direction and will be the head of the direction? Okay, the tail of the direction, every direction will be at origin of a unit cell, and the head will be at this point, governed by the Miller indices. Okay, the tail will be at origin always, but the head coordinates will be determined by the Miller indices. Alright, so these are actually the head coordinates of our direction that we are finding out here, and the tail will be at origin. After differentiating them, after separating them into coordinates, the second step is to divide by the LCM of the non-zero Miller indices. This is something that you can do in rough work as well, because here LCM that you will get, non-zero indices are 1 only. These are 0, 0, so their LCM will not be taken. So it's simply 1. LCM is 1. We'll divide each of the index by 1. The importance of this step will be clarified in the indices where there are other numbers uh, than 1. Okay, you will see its influence in this direction and others directions, because this is a really important step while drawing the directions from Miller indices. Okay, we have to divide the LCM of non-zero Miller indices. So we did it here, and it's 1 again, it's 0 and 0. So these are the final head coordinates. Final head coordinates are 1, 0 and 0, separated by comma signs. The head coordinates, now let's draw them. For drawing, we'll draw the unit cell first, because the direction needs to be drawn inside a unit cell. This is the unit cell, and you don't need to draw the atoms yet. This is the x axis, y axis and z axis. When all of the indices are positive, this is the origin. Okay, and these are x, y and z axis. When the indices are negative, you have to shift the origin. This is a really important thing to remember. So we have tail at origin, this is the origin, and head at 100 position. Okay, and these are the x coordinate, y coordinate and z coordinate. They show that how much we have to move, okay, along 3 of the axis lines. So let's start moving first along x-axis, and from origin we'll start moving 1 unit along the x direction, which means to the other corner of the unit cell along the x direction. This is the x direction, and 1 means to the other corner of the unit cell. 1 by 2 means halfway to the, this is the whole one length, one corner to another corner, and this is half of it. Okay, this is how we take the numbers. So 1 means to the other corner of the unit cell along the axis direction, which is this point. After that, we can see no motion along y direction, no motion along z direction. 0 shows that. So this is the head coordinate, final head coordinate. So we'll join the tail with head, and we, for head we can make a vector on it, show it's a head. Okay, this is the direction 100 direction. Alright, this is the 100 direction, and since it's a cube, let the length of the cube be, let the lattice parameter be a. Lattice parameter means the cube length from one corner to the other corner along the axis directions. Along the axis direction means this is the axis direction, so one corner to other corner is a, but this is not axis direction, this is not parallel to axis direction, so this length will not be equal to a. So lattice parameter is actually this. Let the lattice parameter be a. Okay, now what is the length of the line here? That is capital L, that is equals to, length of the line is simply a. You can see from one corner to the corner, this is actually the direction, and it's a simply. So length of the line is simply a. Now what are the net number of atoms lying on the plane? We need to calculate it, and for that purpose let's draw the atoms that we know that are here. So there will be one atom here and one atom here. In simple cubic, both of the atom touch each other. Okay, and clarify it, okay, because this will help you to find out the relationship between the lattice parameter and the atomic radius later on. Just just an additional information that which atoms will touch each other in simple cubic. In simple cubic, all 2 atoms will touch each other which are along the axis direction. Okay, while all other atoms will not touch each other, only those which are along the axis direction, which means I'm taking these center points so that I'm drawing them right. Perfect diagram. I'm just making these center points, and let's make an atom joining these two together, then joining these, then Okay, now here you can see that this is axis direction, x parallel to x direction, and it's also x-axis, so these two atoms will touch each other. This is parallel to z direction, so these two atoms will touch each other. This is parallel to x direction as well, they will touch each other. This is parallel to z direction, these two atoms will touch each other, but these two atoms which are on this line, they will not touch each other. Okay, though this is radius capital R, this is radius capital R, but there will be distance between them. Just to clarify you people, because sometimes we normally draw rough diagrams in calculation of linear densities, but it makes sometimes confusion when we are calculating the relation between atomic radius and the lattice parameter. Okay, so that is something that I just wanted to tell you people, that only these axis directions atom will touch each other, none of the other atoms will touch each other. If in diagrams they are touching each other, so it's by mistake or that's random, it's not a problem at all, because that's not the point of the problem. You should just know it. All right. Additionally, these axis lengths from one corner to the other corner of the unit cell are always a in cube. Okay, like this, from one corner to the other corner of the unit cell, this length is a. This is parallel to x direction, so this length will be a. All these lengths, all these highlighted lengths that you are seeing are a always. The lengths other than these lines, okay, since they are parallel to x, y and z direction, they will always be a from one corner to the other corner of the unit cell. But if it is like this length is not parallel to x, y or z direction, this is making some angle, so this length will not be a, it will be something else that we need to calculate. And lastly, one last more thing, important thing to remember is that all of the corner atoms, their center will be at the corner of the unit cell. Okay, all of the atoms which are at the corner of the unit cell, the atom center, the atomic center is at the corner of the unit cell, which means that the distance of its this point, this corner point to any point on the circle will be radius. Okay, it will help you to calculate the net number of atoms lying on the plane. Okay, these are the crucial things to remember. From the center to the any point on the circle is always radius or half the diameter. The first thing I have mentioned is true for simple cubic only, like that touching process, while the other two things that I have mentioned is true for every cube you are considering only. Okay, so let's continue with our problem. And how you people will calculate the net number of atoms and how you will assign a number to it. Let me clarify this thing to you people. If the whole atom's diameter, this is the whole atom, if the whole atom's diameter, which is this length in whatever direction, whole atom diameter, if it is intersected by the direction, like if this is the direction starting from like this point for example, or like that, if whole of the atom's diameter is intersected by the line, then you will take the atom's contribution to the line as 1. This atom's contribution to the line will be considered as 1. If only half of the diameter is inside the line, for example this is the half of the diameter, this is complete diameter. I hope you know what diameter is. Diameter is from one corner to the other corner of the circle. Okay, so which are in front of each other. So this is the half diameter. If the length, if this is the direction and only half of the diameter is inside the direction, then you'll take its contribution to the line as half. Okay, if for example this is half of diameter and this is 1/4, if only 1/4 of the atom's diameter is inside the line, then you will take the atom's contribution to the plane as to the direction as 1/4. Okay, this is how you will decide and assign number to the contribution of atom to the line, that how much, what fraction of its diameter is inside the line. Okay, what fraction of its diameter is inside the line, and you will do it separately for all the atoms and you will add it up. Okay, so let's do it here. You can see this is the line, this is the complete line. Okay, and you can clearly see this is the center of this atom. Okay, center of the atom is here, and only half of the atom's diameter is inside the line by this atom, so its contribution to the line will be half. Okay, for this atom only half of its diameter is inside the atom, and for this atom same is true, only half of the diameter is inside the line. You can see this is the whole diameter, only half atom's diameter is inside the line. That is why you will take this atom's contribution to the line as 1/2 as well. Okay, so it's half by this atom and half by this atom. You will add it up to get the total number of atoms lying on the line. That is simply depending upon the fraction of atom's diameter that is lying on the line. That is really simple. You have to just remember this simple thing, and you write 1/2 plus 1/2 here, which is equals to 1. Okay, and now the linear density is given by linear density is equals to 100 is equals to 1, which is net number of atom lying on the line, divided by a. 1 over a. This is the linear density in terms of lattice parameter. If you want to calculate the linear density in terms of atomic radius of the atoms making up the simple cubic unit cell, then what you can do is to use the relation between a and atomic radius for simple cubic structures, which is always true for simple cubic structures. Here you can see this whole length is a. You can easily find out the relationship between the lattice parameter and the atomic radius. Here you can see this is the lattice parameter, which is completely a, and this is 1r and this is 2r. Okay, this is 1r and this is also r. This distance is r and this distance, so it's total of 2r. Okay, for simple cubic structures, this relation is always true, that the lattice parameter is equals to the double of the atomic radius. So you can simply put it right here to get the linear density in terms of atomic radius. Okay, both of them are correct. So because sometimes for numericals you need to calculate linear density, you need to know the linear density in terms of atomic radius or else whatever it is. So this is the final result for the linear density of 100 direction, and its units are atoms per meter. Okay, for example, the result you get is 3 multiplied by 10 to the power 6. So it is equal, its unit will be atoms per meter. Atoms shows that these number of atoms are there per meter in this direction. Okay, so atoms is not something, it's just showing the its number of atoms. You can even use this thing like per meter, but it's better to use atoms per meter to show that it's atomic density, atomic linear density. All right, so this is it. Now let's do it for the other directions. Now let's calculate the linear density for this direction 110 in simple cubic unit cell. The first index shows the x coordinate, the second index shows the y coordinate, and the third index shows the z coordinate in these Miller indices. So x, y, and z. For x, we'll write the first one, which is 1. For second, y, we'll write 1. Third is 0 here. Now, after separating them into 3 coordinates corresponding to x, y, and z, we divide each of these indices by the LCM of these indices. Okay, this is an important step to do. Since in our case it's 1, 1, will not take zeros. Okay, zeros are not considered. We'll take non-zero numbers only. So it's 1 1, and LCM of 1 1 is 1, and dividing by 1 doesn't make any difference. That is why the importance of this step is not shown in this case, but it will be shown in other cases when we'll have other numbers in the Miller indices. Okay, so that's an important step, to divide each of the indices by the LCM of the indices. And after doing this, the numbers we get are the head coordinates of the direction. So we have these head coordinates 1, 1 and 0 corresponding to x, y and z. These are the head coordinates of the direction. So why I'm saying head coordinate, because if we see what our direction looks like, it is like it has two main points. One is tail and the other is head. Okay, while drawing the directions from given Miller indices, the tail is always at the origin of the unit cell. We always set the tail of the direction at the unit cell origin, and the head coordinates are determined by the Miller indices. So these are the head coordinates, while the tail will be at origin simply. So let's draw this direction, and after drawing this direction, we could determine all of the parameters that are needed to calculate the linear density. So first of all, let us draw the cube, and we don't need to draw the atoms in it. Okay, we'll draw only those atoms which are potentially lying on the line. Okay, so since all of the indices are positive, that is why this is the point as origin. This is called as the all positive origin, when all of the indices are positive. When any of the index is negative, then you have to shift the origin appropriately, so that, but this video is not for guiding you to draw the directions from Miller indices. Okay, I'm just mentioning it. If you want to learn it, I'll link the video in the description box if you are interested to learn a complete method to draw directions from given Miller indices, where I have did it for a variety of of directions. So this is our coordinate system. This is x-axis, y-axis and z-axis. The tail is at origin. Okay, this is the tail. Now let's find out where the head is, where the head point is, and these are the head coordinates. One means from one corner to the other corner of the unit cell along the axis direction. So this is x-axis, this is x direction, this is for y direction, and this is the motion for z direction. These are actually showing what motions needs to be done. Okay, so starting from the motion along the x direction, and we'll start from origin. It's 1, which means to the other corner of the unit cell along x direction, which is this direction. So this is the other corner of the unit cell. Now what next is y direction, and we can see it's 1 for y direction. 1 unit means to the other corner of the unit cell along the y direction. So from this point onwards, okay, from this point onwards, we'll move 1 unit along y direction to the other corner of the unit cell, which is this point. And next we have z coordinate, which is 0, which means no motion along z direction is needed. This is the final point. This is the final point. This is actually a map. This gives you a map that how to move and where to move to reach a specified point. All right, in case of planes, the method is different, because in planes, Miller indices shows intercepts, while in directions, Miller indices shows the coordinates, and coordinates are actually the map uh, to the final location. And this is the final location. Now let's join these 2 points together, and this is the tail and this is the head. So this is the direction, and this is direction 110. All right, now we need to calculate the length of this line as well as the total number of atoms lying on this line. First of all, we'll find out the length of this line, because it's really easy. As you have seen in the previous part, I have shown you the important steps, that important things to remember, that this length is a, this length is a, this length is a, this length is a. All the lengths along axis direction from one corner to the other corner of the unit cell are always a. So this length is a, this length is a, but this length is not a because it's not parallel to x, y, or z direction. It's making some angle. So we need to calculate, and we can calculate it using the Pythagoras theorem. Okay, so I'm calling it as L because it's actually the length of the line. So using Pythagoras theorem, it is the hypotenuse base perpendicular. L square equals a square plus a square, which is equals to 2a square. L square equals 2a square, and taking under root on both sides gives L equals under root 2a square equals under root 2, and a will come out because it's square and under root cancels out. So L equals under root 2a. Alright, in our case this is the length, and now let us calculate the net number of atoms lying on this line, and it's really easy. Let us draw the atoms. There is one atom here and there is one atom here, and as I told you people, let me recall that all the corner atoms, the atoms which are at the corner of the unit cell, the center of the atom is at the corner point. Okay, which means this is the center of the atom as well. This is the center of the atom, and from center to the boundary, is half the diameter, okay, or radius of the circle you can say, but half the diameter because this is how we will take the contribution of the atom. So if, let me clarify and recall, if this is the diameter is actually double the radius, and we take the contribution of an atom to the line as 1 if the whole diameter of the atom is inside the line. If whole the diameter, this diameter length L, because it's linear density, so we are finding out the contribution of atom to the line in terms of diameters. Okay, in case of planes we compare it to the area or the angle, total angle of the atom. In case of planes the metric becomes different. In case of linear density we take diameter as a metric, like what fraction of diameter is inside the line. Okay, if whole of the diameter is inside the line, we take its contribution to the line as 1. If only half of it, for example this is the line and this is the atom, and only half the diameter is inside the line, then we'll take its atom's contribution to the line as half. Okay, and if we have, this is half diameter line, okay, and this is 1/4 part, this is half and this is 1. So let's say the line is like that, only 1/4 of the atom is inside the line, then the atom's contribution to the line will be taken as 1/4. Okay, if you understand this, you can do and calculate linear density for any kind of cube. Okay, whether it is BCC, FCC, or simple cubic, the rule is same. So here you can see this is half the diameter. Half the diameter means the radius because it's center of the atom to the corner is radius, so it's half contribution by atom to the line, and this is half as well because only half the diameter is inside the line. You will not be considering the whole circle or anything like that. You'll just take the diameter terms, since this whole length would have been the diameter and only half of it is inside the line. All right, so half by this atom, half by this atom, so the net number of atom lying on the line is 1/2 plus 1/2 equals 1. Okay, now let's find the linear density for this direction by putting the values into the formula number 1, which is capital N by L. Okay, let's put values here. It's 1 divided by under root 2a. Okay, and we know the relation between a and capital R is a is equals to 2 capital R. So we'll direct, this is the relation for simple cubic unit cells. It's always true for simple cubic. Okay, so we'll put the value of A right here to get the linear density in terms of atomic radius. This is the linear density in terms of lattice parameter. This is the linear density. After inserting its value right into this expression, we'll get the linear density in terms of the atomic radius of the atoms making up the unit cell. So this is the linear density of simple cubic unit cell in terms of atomic radius of the atom making up the unit cell. All right, and this is equivalently in terms of lattice parameter. Units are again atoms per meter. By slash we means that it's in denominator, or you can simply write atoms with a space per meter. Space is needed to differentiate that they are separate terms. Okay, so for example, you get 5 multiplied 10 to the power 6 as the linear density. You'll write units as atoms per meter or like that. Okay, this is how you'll write it. So this is done for 110 direction. Calculate linear density for this direction in simple cubic unit cell. The first step is to draw the direction inside a unit cell, and I'm repeating these steps again and again because some students just jump directly into particular parts of the video because they need, for example, linear density for that direction only. So that is why I'm repeating the steps and important points again and again so that you may not get confused. First step is to draw the direction. This is the first index and it is for the x coordinate. Okay, second index is for the y coordinate and the third index is for the z coordinate. Okay, now let me clarify that what is direction. Direction is shown like that. It has a tail and a head. This is head and this is the tail. Okay, so the direction that we are gonna draw will have tail at origin of the unit cell and its head will be decided and determined from the Miller indices. Okay, the process that we are going to do here will give us the coordinates for the head of the direction while the tail will be at origin. All right, so let's find out the head coordinates. So we have 1 here, 1 and 1. Next step is to divide these Miller indices by the LCM of these Miller indices. If it contains 0, then you will neglect 0. You will not include 0 in here. For example, in case of 1 1 0, you will not include 0 in LCM. So 1 1 1, it's 1 LCM, so you will divide each of the index by 1 and you will get 1 again. This is an important step. You will see its importance in 112 direction, for example, the next direction that we will be dealing with. So that's an important step. Don't ignore it, remember it. And these are the final head coordinates, 1 1 1. This representation separated by comma sign is for the coordinates. Okay, so while this, where there is no comma in between them, this is for the Miller indices of planes. Okay, this is representation for planes Miller indices. Now let's draw it. For that purpose, we'll draw the simple cubic structure first, and we don't need to draw the atoms. We'll only draw those atoms which potentially lie on the line. We don't need to draw all of the atoms because it's not needed and it will just complicate the drawing. Okay, that's not needed. Since all of the indices are positive, this point will be taken as origin. If the indices, if any of the index would have been negative, then the origin needs to be shifted. We'll see if we will calculate linear density for any direction which has negative Miller indices. We'll do that later. So this is x axis, y axis and z axis, and the direction tail is at origin here. This is the tail, and head is at 1 1 1. These coordinates shows what motions along axis is needed to reach that point, to reach that head point. Okay, so let's start moving from origin along x direction, and we need to move by 1 unit. 1 unit means from one corner to the other corner of the unit cell along axis direction. Axis direction is x-axis, so along x direction, which is this direction, to the other corner of the unit cell, which is this point. Now from this point onwards, we need to move 1 unit along y direction, since y coordinate is 1 again. So from this point onwards, we'll move 1 unit along y direction. So this is the y direction, parallel to y direction. From this point onwards, for directions, you will move onwards from the point you left. So this is 1 unit. Then we have 1 as the z coordinate, which means from this point onward, we'll move 1 unit along z direction, which is this direction. Vertically upward, you'll move like that, and this is the final point. This is the head of the vector. So tail and head will be joined together like that, and this is the direction. Okay, this is the what direction it is. It is 1 1 1 direction. Now we need to calculate its linear density, and for that purpose we should know the length of this line and the net number of atoms lying on the line. First, let's calculate the length of the line. For that purpose, let's make a triangle. We have this hypotenuse, we have this perpendicular, and base will be this. Okay, this is the base. Let's call it B. This is L that we want to calculate, and this length is A. All the lengths from one corner to the other corner of the unit cell along axis directions will be A. Okay, this is parallel to axis direction, but these lengths are not parallel to axis, any of the axis direction. That is why their lengths will not be A, something else we need to calculate. And for knowing L, we should know A and B. B is not known. Let's first calculate it, and for B, we will consider this triangle. This length is A, corner to the other corner along axis direction. Since it's A, then this length is A again for the same reasons. So let's apply the Pythagoras theorem. This is the hypotenuse, this is base and perpendicular. Base square equals A square plus A square, since both of the lengths were same. So B square equals 2A square. B equals under root 2A. Okay, you will take under root on both sides. The under root on A will be cancelled because it has square on it. Square and under root cancels, and it's A, and under root 2 comes like that. So B is under root 2A. Now using Pythagoras theorem in this triangle, so hypotenuse is L here now. For this triangle, L square equals A square plus B square, which is under root 2A square. Let's simplify. Square of under root 2 is 2. Square of A is A square. It's 3A square. And L will be equals to taking under root on both sides. It's under root 3A. Length of a line is under root 3A here. Now let's find out the net number of atoms lying on the plane. Lying on the line. We have calculated the length of the line for 1 1 1 direction. Now I'm gonna find out the net number of atoms lying on the line separately, because I lost that page. I couldn't continue at that moment. I got busy. So let's continue. We are about to find out the net number of atoms lying on the line. So this was the direction 1 1 1. This was the origin, and again the same thing. We'll have these two atoms. One is at this corner and another here. Okay, this is the center of the atom, and this is the center of the atom. None of the other atom will lie on this line, and you must be noticing that net number of atom lying on the line for all the directions we have considered is 1 till now. We'll see what's gonna happen with 1 1 2 direction. We'll see it. Super easy as well. We can see only half of the diameter of the atom is inside this line, so its contribution to the line will be 1 by 2, and only half of it is also inside the line. Only half of the diameter of this atom is inside the line, so half contribution by this. So capital N is equals to 1 by 2 plus 1 by 2, which is 1, and N equals 1. So let's find out the linear density for this direction, and it is equals to, by this ratio, N by capital L n was 1 and L was under root 3a. Okay, so now this is the linear density in terms of lattice parameter. Now let's calculate, now let's convert it into atomic radius. Atomic radius, for that purpose we'll just put A equals capital 2r. Okay, this is the relation between the lattice parameter and the atomic radius that is true for simple cubic unit cell only. Okay, so we'll directly put right into this expression because we know it, and we even calculated it for during the while finding out the linear density of 100 direction. So I am not repeating it again. 1 over 2 under root 3 capital R, this is the linear density of simple cubic unit cell for 111 direction. All right, units are same, units are atoms per meter, or simply you can write atoms with a space in between per meter. Okay, these are the units of linear density, whatever answer you get. For example, if A is equals to 5.1 angstrom, and 5.1 angstrom is 10 to the power minus 10 meter, you will put it right into this equation. The result you will get, for example, you put it in the denominator and the answer you got is, for example, 2 multiplied 10 to the power 10. Then you write atoms per meter as its unit. Okay, sometimes it's a kind of problem related to it. So I hope you got it. This is the linear density in terms of lattice parameter for this direction. This is in terms of atomic radius for this direction. Let's calculate the linear density for 112 direction in simple cubic unit cell. First of all, we need to draw this direction inside a simple cubic unit cell, and for that purpose we have the first index which shows the x coordinate. Then we have second index which gives us the y coordinate, and then we have the z coordinate, sorry, z index which gives us the z coordinate. Now after separating them, what we have to do next is to divide the LCM of the Miller indices by each of the Miller indices. Okay, so let's take the LCM of these Miller indices in a rough work. Okay, we have Miller indices 1, then we have 1, and then 2. Only non-zero Miller indices are taken. So 1 times 1, then we have 2, 2 ones are 2, so 2 into 1 is 2, so 2 is the LCM, and we'll divide each of these indices by 2, and after dividing we got 1 by 2, 1 by 2, and 1. These are the head coordinates of a direction. Okay, while the tail will be at origin. The tail coordinates will be, if you want it to write it, since it is at origin, so the tail coordinates are 0, 0, 0, and the head coordinates of a direction are 1 by 2, 1 by 2, and 1. All right, if we see a vector has a tail and a head. So the tail will be at origin. Whenever we are drawing the direction from given Miller indices, we'll set the tail of our vector at the origin, while the head will be at the point determined from the Miller indices. Okay, so these are the head coordinates and tail will be at origin. Now let's draw the unit cell and draw this direction inside it, because we know the coordinates now. It's really easy next to do that. And this is, I'm gonna use different colors so that you may distinguish between each of the wall. These are the walls. This orange one is the front wall, the green one is the back wall. Since all of the indices are positive, so this is the all positive origin, and this is the x-axis, y-axis, and z-axis. Okay, and this is the tail. Now let's see where the head of the vector is, and for that purpose we'll use this map. This is actually the map. It tells us what motions to do along which directions to reach the head point. Okay, so first is starting from origin, we'll move half unit 1/2 unit along x direction. Half units mean this whole length is 1, half of it is here. Always do it by taking the whole length and dividing it by 2. Don't just do it randomly like this or this. It makes it more accurate if you take the whole length as 1, then take the half of it is 1/2. We reached here. This is 1/2 along x direction, positive x direction. Then we have 1/2 units along y direction. From this point onwards, we need to move half unit along y direction. This is from this point onward, this whole motion will be along y direction, and from this point to this point is 1, and half of it is here. Half of this whole length, don't confuse it with these lengths. Half of this length, because this is where we need to move to the other corner of the unit cell. So this is half point. So this is half and this is half along y. So half along x, then half along y. Next is to move 1 unit along the z direction. It's 1 unit along z direction, which means vertically upward. Vertically upward. Will be here. It's on the roof. Okay, at the center point of the roof. This is at the center point of the roof, because we can see that is half and half. It means this is at the center point of the floor. Okay, and this is the center point of the roof, perfect center of the roof, so that you may imagine the atom. So this is the head coordinate and this is the tail. Joining them together gives us the direction. Now let's find out the net number of atoms lying on this line, and that's really easy. We have this atom here at this corner. Now none of the other atoms is lying on this line, because if you draw this atom, it will just touch this point, but it's none of its part is inside the line. This line is here, and similarly here, if you draw it, none of the other atoms will be lying on this line. Only this atom's contribution will be to the line. Okay, so it's half. Clearly you can see only half the diameter of this atom is inside the line, so it's half contribution by this atom to the line. All right, so we can see the net number of atoms lying on the line is 1/2 only. Now let's calculate the length of this line, and let me give you a really easy method other than the one we have previously used. Previously we used Pythagoras theorem to calculate the lengths of the line, but there is another method, really easy method, that is free of any confusions. So we are gonna use distance formula to calculate the length of the line. Okay, you could have used the distance formula for the previous cases as well. But you should learn multiple methods. That is why I'm just gonna use this method here, and if it is more easier to you, then use it for other cases as well, whatever it is convenient to you. So in distance formula, we should know the head coordinates and the tail coordinates that we already know. So in distance formula, the length of the line L is equals to under root of x2 minus x1, these are head coordinates, minus tail coordinates, x directions, plus y2 minus y1 square plus z2 minus z1 whole square, and this whole multiplied by a, which is the lattice parameter. We have to multiply a because there are lengths in a parameter, so a will be multiplied outside of the square root. Now let's put the value right here. X2, this is x2 and this is x1, y2 y1, z2 z1. Since they are all 0, their subtraction from the head coordinate will not be, will not bring any difference, but let's do that for the sake of following the method. 1 minus 0 whole square to a, then it's 1/2 whole square, which is 1/4, plus 1/2 whole square, 1/4, plus 1 minus 0 is 1, 1 square is 1, into A. 1 by 4 plus 1 by 4 is 1 by 2 plus 1 into A, which is equals to under root 3 by 2. You will take LCM. 1 by 2 plus 1 is 3 by 2 into A, and you can simply write it as L equals under root 3 by under root 2 into A. You can separate the LCM. Oh, you can separate the square roots. Square root on 3 is separated and 2 is separated. It's easy. And now let's find out the linear density by dividing n by capital L. N is 1 by 2, and here we have under root 3 by under root 2 into here. A is then here with let me do it here. 1 1 2. N is 1 by 2 divided by, this is always a savior, it will avoid any mistakes. So under root divided by under root 3 by under root 2 into A. Okay, when we change the division sign to multiplication sign, inverses happen. So under root 2 in the numerator and under root 3 into A denominator. So under root 2 by 2, if you do the calculation, you'll find out that under root 2 by 2 is equals to under root 1 by under root 2. Then under root 3 into A, and we can put them in single under root, and it's 1 over 2 into 3 is 6, 1 over under root 6 into A. So the linear density is 112 1 over under root 6 A. This is the linear density in terms of lattice parameter. We can convert it into atomic radius, because in simple cubic we know that A is equals to 2R. Okay, this is the relation that is true for simple cubic unit cells, and I have justified it in a part where I'm calculating linear density for 100 direction. You can check out that part if you are interested in knowing that how it is true. So 1 over under root 6 into 2 capital R, and it's equals to 1 over 2 under root 6 capital R. This is the linear density of 112 direction in simple cubic unit cell in terms of atomic radius. So it's 1 over 2 under root 6 capital R. Okay, so this is the final result, and this is the final result in terms of lattice parameter, in terms of atomic radius, and the units are same, atoms per meter. Atoms per meter. For example, if you get result of 5 multiplied 10 to the power 8, so you write units as atoms slash meter, which shows that meter is in the denominator because R is in the denominator. Or you can use 5 multiplied 10 to the power 8 atoms space per meter, like that. Okay, atoms is written to show that this is a linear density, linear atomic density, because it's number of atoms per meter length. Okay, and if you count something, it doesn't have any unit properly, basically. Like if you count atoms, if you count toffees, so it's 12 toffees. Toffees is not a unit, it's just showing that what you have counted. So here writing atoms is just to show that what you have counted, you have counted atoms per meter length. Okay, so that is why we are writing atoms. It's better to use like that, but it's okay to use it like that as well. But space is needed, and that's all. I hope you got it. Like, share and subscribe, and if you have any questions, you can ask me in comment section. Goodbye.